This is your presenter Asloob Mudassar, and I am presenting slide number 3 of the course on laser physics. Question: what are the absorption, spontaneous and stimulated emissions? Answer: an atom or a molecule can accept energy from outside world in many ways. With respect to laser point of view, particularly when active medium is in gaseous state, the particles, for example the atoms or molecules of the active medium, can accept energy from energetic electrons hitting the species or from the electromagnetic waves interacting with them. Absorption is a process in which particles of the active medium accept energy from electromagnetic waves. When the photon energy matches exactly with the energy gap between any two levels which exist in the particles of an active medium. An incident photon is absorbed by a particle of the active medium and the particle is said to be in the excited state. Absorption is thus the excitation of an atomic or molecular component of an active medium through the absorption of a photon. When the energy of a photon matches with the energy gap between any two levels of the particles of an active medium, the levels are said to be in resonance with the photon energy. Absorption is sometimes referred to as stimulated absorption. An excited particle may radiate its energy in any direction by giving up the photon of the same energy as that of the incident absorbed photon. The process in which an excited particle comes to a lower energy state by giving up energy in the form of a photon is called spontaneous or radiative emission. If E1 and E2 are the energies corresponding to two levels of the particle under considerations, with E1 less than E2, then the frequency nu0 of the emitted radiative wave or photon is given by nu0 is equal to E2 minus E1 over h. This is equation 3.1, where h is the Planck's constant. There are other ways in which an excited particle may come to lower energy state without emitting a photon or without radiating electromagnetic energy. Such processes are called non-radiative decay processes. This is the figure and the caption is illustration of absorption, spontaneous and stimulated emissions. The first one is the absorption. Atom in state 1 is shown on the left side with the energy E1 and E2. That is, this atom has suppose that has two levels, the level with the energy E1 and the level with the energy E2, and the electron is initially in the energy state E1 and an incident photon is incident on it. So the electron will, if the energy of the photon matches with the energy gap between these two levels, then this photon will be absorbed by the electron in state E1 and will move to the state 2 as shown on the right hand side, that is the atom in state 2. And you see that there the electron is in energy level E2 because it has absorbed an energy and has moved from electron and have moved from energy state E1 to energy state E2, and the atom in state 2 is said to be in the excited state. Now let's talk about the spontaneous emission. Again, continuing from the state of the atom in state 2, where the electron is in the energy state E2. This electron will radiate its photon in any direction. So the photon will be radiated in any direction and the atom will come back to its initial state, that is the state E1, in which the electron is revolving in which the electron is in state E1. So this is the spontaneous emission in which the energy of the photon is radiated in any direction when the de-excitation occurs. Now let's talk about the stimulated emission. Again, starting from the atom in state 2, that is the atom is in the excited state, or equivalently the electron is in state E2. and an incident photon of energy which is equal to the gap of the energy between level E1 and E2 is incident on the atom in state 2, and this incident photon stimulates the atom to emit its photon in the same direction, that is in the direction of the incident photon. And you will see that on the right hand side, in the stimulated emission, on the right hand side the atom comes back into the state E1 by giving off its photon. And now this photon is not radiated in any direction, but it is radiated in the direction of the incident photon. So both the photons, that is the incident photon plus the stimulated photon, travel in phase along the direction of the incident photon. So in the stimulated emission, the difference is that the photon which is emitted by the atom during its de-excitation process, the photon is emitted in the direction of the incident photon. Whereas in the spontaneous emission, the radiated photon could be emitted in any direction. An active medium consists of a large number of particles, some of them in the ground state, that is level 1, and some of them in excited state, that is level 2, in a two-level particle system. If a pumping process is there continuously feeding energy to the particles of the active medium, the particles will absorb energy and will move to the excited state, that is level 2. The excited particles may start their journeys to the level 1 through spontaneous emission, in which radiative energy is given in random directions. In the very beginning, a small number of spontaneously emitted photons may travel along the axis of the resonator through the active medium, and during their course they may interact with excited particles. If this interaction occurs before the excited particles decay spontaneously, the photons incident on the excited particles will stimulate them to emit their photons in the direction of the incident photons. The de-excitation of an excited particle through the interaction of a resonant photon, that is the energy of the incident photon, is the same as that of the excited particle, then this process is called stimulated emission. If h nu naught is the energy of the incident photon, then the energy of the stimulated photon will also be equal to h nu naught, and both these photons will travel in phase and in the same direction, that is the crests and the tufts of the two photons will exactly match each other during their propagation. The three processes have been explained in the figure Q3.1. This is the end of slide number 3.